so I can get this actual process in here. There we go. So say we want to search this list for 8. Well, the first thing we have to realize is essentially the XY that we have is the 1, 3, 8, 9, and the 12, 16, 25, 30. So what the recursive step tells us is that we're going to break this up into search 8, you know, essentially that list, 1, 3. I guess you could give it a name, but how many parentheses do I need here? Or search 8, 12, 16, 25, 30. This one is going to be a bit tedious to write out. I understand that. But so essentially that's how the first step would go. And then you would have to do the recursion again on each one of those pieces where essentially your XY is the 1, 3, 8, 9, and then 12, 16, 25, 30. Then you have to break it up again before you can actually use the true false statement. So that's how that'll work. And then the execute in order T, if you watched the videos, you should know how that works. So hopefully you watched the videos. So I'll give you a couple minutes to try those while I pass some stuff back to the people who are here. Don't worry, I'm going to put it back together in a second. Oh, that's going to move too much. It's going to move way too much. Oh, well, I'll rewrite it. Ah, stop. Yep, there's a quiz today. All right, so let's talk about this. So that doesn't have enough parentheses. So again, so we're starting with this S list, and so let me talk about the S list one more time. So this is the S list we're considering, and essentially it has kind of stages to it. The very first stage is like each number individually. And I mean, well, they're grouped together in like sets of 2. So just to try to make what I'm about to do make more sense. And then kind of the next step is you have to take pairs of numbers and group them together. So you can't just take, so essentially the next step up is 1, 3, and 8, 9. It's essentially like the first step is the very numbers by themselves. The next step up is the thing that you're pairing it with. So we're pairing 1 with 3, 8 with 9, 12 with 16, 25 to 30. And then you have to essentially take those and pair them together. So the next step up would be pairing the 1, 3 with the 8, 9, and the 12, 16 with the 25, 30. So there's kind of like it's like 3 stages deep, if you will. So we essentially are going to then have to essentially use this search function, the recursive step, approximately 3 times. Why does that say 1, 2 instead of BR? It used to say BR. Anyway, so we're going to have to use this recursive step essentially 3 times. So I've already done the first one. So we wanted to do search 8L, which is essentially saying take that list, that S list, and figure out if there's an 8 in it. And again, I know you can stare at it and there's an 8 in it, but so you're a computer and you don't have eyes. So what we have to do now is we broke up the first thing. We essentially took that kind of third step deep, if you will, and we broke it up into the 2 pieces that gives us. So now what we're going to have to do is, well, let me kind of match my colors here. If I put it in blue over there, let me put it in blue over here. So now we essentially have the pairs 1, 3 paired with 8, 9, and 12, 16 paired with 25, 30. So we have to use that recursive step on both of those to break that up one more time. So we're going to have search 8 on 1, 3, or search 8 on 8, 9. That breaks up that first, this piece now became this piece. Or, so essentially that or is the or from the line before. Just doing lots of colors to try to figure out where these things came from, or keep track of, shall I say. And then we have to break up that second search into search 8, 12, 16, or search 8, 25, 30. So this search turned into these 2 searches. Is that okay? All we're doing is following the directions from the definition of the function. Questions before I get going? Okay. My goal is to essentially get down to this true-false idea. I can't do that until I'm considering just a single number in the second part of the search. So I have to break it up again for each of them. I think I'm going to run out of space. But here we go. We're almost done this one. We've got to break it up one more time, and then we can finally do our true-false statements. So we're going to have that first one is going to break up. The one on your quiz is not this long. Search 8, 1 and search 8, 3. So we essentially broke that 1, 3 up into its two pieces. Or search 8, 8 or search 8, 9. So I've essentially taken that thing that was underlined in the yellow and broken it up into its final pieces. So I've only written half of it. And now I have to break up the other side respectively, kind of in a very similar way. So we have or search 8, 12 or search 8, 16, run out of space. Let me try to zoom out and kind of squeeze it. Or search 8, 25 or, oh no, a little bit more. Search 8, 30. So I know this one was pretty tedious. The one on your quiz is going to be in terms of S lists, but it's going to be about half the size of this S list. So, it'll only be two recursive. Am I lying? I'm not lying. There's only 2 recursive steps instead of 1. It's not the same function. It's very similar, where you break it up at the certain pieces until you get down to the step where you can do the actual thing for a single number. But it's not going to be actually the search one. But very, very similar to what we're doing here. So now that we have just one number in the second piece of all of these search functions, we essentially go to the base case, which is telling us, so search, now that I've zoomed out, let me rewrite it. So search a number for a single number, if you will. So I put X instead of L. Well, this is essentially going to be true if T equals X and false if T does not equal X. So I know I'm running into the other one. I'm really sorry. This is a big question that I'm trying to do here. So essentially, search 8, 1 would be false because 8 is not equivalent to 1. Or search 8, 3 is false because 8 is not equivalent to 3. Or search 8, 8. 8 is equivalent to 8, so that's true. Or search 8, 9, false. Or search 8, 12, false. Or search 8, 16, false. Or search 8, 25, false. Or search 8, 30, false. Oh, it lagged a little bit. So that's kind of why the ORs came into play. Because essentially, if we want this whole thing to be true, we just need one of those pieces to be true. So there was the piece in kind of that third one that did turn out to be true. So this entire thing is true. Essentially, 8 did show up in that list, which again, I know we already knew from the very beginning, but that's how the function would show us that it is true. So with these S lists, they kind of come in pairs, and the functions you'll be given will be splitting up the pairs until you're down to one number in each situation, and then you'll have some kind of base case that tells you what to do with that one number. Questions, concerns on that? That's kind of what 3.5 was all about. I know we didn't do a search function in the notes, but that's kind of what 3.5 is about, is here's a recursive function. Can you follow the directions enough to use it? What up?
Would you like for us to write, if it's something like that, to write every individual step, or could we just skip to the last step if we are?
So I do want you to write out all the steps, but that's why I'm only giving you half the size of that. So it's true because essentially what we got at the very end was we got a string of either true or false things. Now, because they're all separated by an or, if you think way back when to the very beginning of the class when we were talking about logic and ands and ors and implies and all that jazz, if you have a collection that are separated by ors, if you want the entire thing to be true, you just need one of them to be true. So since there is a true in there, the whole entire string is true. Now, if they were ands, it would be false because then you would need all of them to be true. But since they're separated by ors, we just need one of the things that are stringed together to be true. So since one of them was true, the entire string is true. And that string was true. Maybe that was the question. That string was true. So it was the third one deep, which was the search 8, And our function says that the search something other thing is going to be true if those two numbers agree. Since 8 equals 8, that one gave us true. Whereas opposed to every other one, we were comparing 8 to some number that wasn't 8. So we had a bunch of false, but then that one that was search 8, 8 turned out to be true. So the whole entire string turns out to be true. That makes sense? Yeah, kind of similar. It's not the exact same function, but it works very, very similarly, I promise. You break it up into these pieces like we just did, and then at the very end, it'll tell you what to do with just the one number. But yeah, it's about half the size. It's only like, I can't write in white, that won't work. It's only about this big, not enough.
What was the binary search tree used for again?
What is it used for? What is it used for? Well, yeah, you use it in math because it's a tree, but it is something like, if you think about, I think we defined it in terms of a, what's the word I want? A like dictionary in Word, if you will.
Yeah, but I just meant like in this problem, like you had it off the side. I didn't know what you were using it for.
Oh, that's a different problem that we're going to talk about right now.
Oh, okay.
Yeah, so that one, let's go to that one now. Let me move it over again now that I got smushed up with this one. Oh no, I need that 4. So yeah, completely different problem. Let's look at this guy. So here we wanted to execute in order t, where t is this binary tree. So this one was in the notes, this function. And remember, essentially, it's telling you if you have a tree where you have, it comes down into 2 tinier trees in order, well, I should name this R for the root, and the entire thing is the tree t. So in order t is what gave us essentially in order of the mini tree on the left, then comma the root, comma in order the tiny tree on the right. Oh, sorry. So it only takes one true thing to make the entire thing true. Yeah, so since we were working with a string of ors, we only needed one thing to make the entire thing true. Exactly. Okay. So if we name this entire tree t, we're going to have that in order t. Now notice we have 2 smaller trees on each side. So I'm going to name it T1 and T2. So the in order function is going to give us in order T sub 1, comma 25, comma in order T sub 2. And then we have to do the in order on the smaller trees. Now the smaller trees are also made up of even smaller trees. So let me call them T1 superscript 1 and T subscript 1 superscript 2. And then over here we have T sub 2 sub superscript 1. And then we kind of have this over here, but it's empty. But I'll name it T2 2. So we'll have in order T sub 1 superscript 1, comma 16, comma in order T sub 1 superscript 2. So this first in order T sub 1 gives us this entire piece here. The 25 just comes down. And then the in order T sub 2 is going to give us in order T sub 2 superscript 1, comma 52. What am I writing? And then in order T sub 2 superscript 2. So this in order T sub 2 in the back, give us these here. And essentially now we're down to that base case of the in order function. So remember the base case of the in order function is, well, you have two base cases for this one. If it was just essentially one vertex, if the tree was just one number, or well, vertex, it doesn't have to be a number, then it's just that vertex. And if the tree was empty, then you just get the empty string, so you just don't write anything for that one. So this would finally reduce to, so in order T sub 1 superscript 1 is essentially 4. We just get that vertex that is that piece. The 16 just kind of falls down. In order T sub 1 superscript 2 gives us the vertex 20. The 25 falls down. In order T sub 2 superscript 1 gives us the vertex 34. 52 comes down. If I want to be sassy, you know, I'll just remind us that that last piece is, well, once it catches up to me. That last piece is the empty string, but you just don't have to write anything for the empty string. So I erased it. There we go. So in order T sub 2 superscript 2 is technically nothing because it's the empty string because that piece was empty. Questions, concerns on that one? So there will also be one on your quiz like that. That is pretty much exactly that, but with words instead of numbers. Okay, I'll wait a couple more seconds in case someone's typing some out. But otherwise, we're moving on to chapter 4. Woohoo! Okay, here we go. Chapter 4. 4.1. Stop. Will it finally allow me to actually just share the, nope, okay, fine then. Be a jerkwad. Alright. So 4.1, basic counting techniques. So we're gonna kind of have to remember some stuff, basic stuff about sets here. So we are gonna kind of go back to the idea of sets for a little bit. So in section 2.2, we learned the inclusion-exclusion principle, which is what's stated below. So if A and B are finite sets, then the size of their union is, so this essentially is this, whoa. Remember the kind of absolute value bars, if you will, is telling you to take the number of elements in that set. So this is the number of elements in the union. Would equal the number of elements in A plus the number of elements of B, but then you have to subtract out the elements in A intersection B, because essentially if you count the elements in A and the elements of B, but they share some of them, you're going to count them twice, so you have to take it out. So, you know, if you have two sets and they overlap a little bit in here, you're going to double count them. But anyway. Now, if A intersect B is the empty set, so remember the empty set is the set of nothing. So if they don't have an intersection, we're going to say that A and B are called disjoint. So in this case, if we wanted, now that thing is called the cardinality. So if we wanted the cardinality of A intersect B, so the number of elements in A intersect B, that would be 0 because it's the empty set. There's no elements in the empty set. And if we wanted to consider the cardinality of their union, since they're disjoints, we can essentially just add the two actual cardinalities together because we don't have to consider this last piece because it's 0. So if they're disjoint, you can kind of just add the elements of each set up and not have to worry about it. So what we're eventually working up, well, no, we'll just see in examples. Never mind. So say a restaurant serves 7 kinds of sandwiches and 4 kinds of burritos, and you only want to order 1 entree for lunch. How many choices do you have? Well, 7 plus 4. But if we think about this in a bit more generality, so you have 7 sandwiches, because it's going to get slightly more complicated than this, of course. 4 burritos. If you consider those to be sets, there's no overlap, right? Well, I guess if you really wanted to consider a burrito a sandwich, we're going to consider burritos different from sandwiches here. We're not going to get into that debate. So we're going to say that there's no overlap between the two. So essentially, they're disjoint sets. The set of sandwiches is disjoint from the set of burritos. So if we want to know how many choices we have, then we just add the number of things together to get 11 choices. Woo! So that's essentially the idea behind the addition principle. Something called the addition principle. So the addition principle says if A and B are finite sets, with the intersection of them being the empty set, then there are, kind of exactly what we already looked at, cardinality of A plus cardinality of B, ways to choose an element from A union B. So that's kind of what we're looking at in chapter 4, at least to start off. We're kind of trying to look at ways that we can choose things. Sometimes we're going to care about the order, sometimes we're not, and that kind of deal. So in this case, if we're just considering, how many choices were there for our breakfast, our lunch, whatever the heck it was, since they were disjoint sets, we could just take the elements of each piece and add them together. So, as I've already said, the sandwiches and burritos were disjoint in that above example, which is very important because not every example we'll look at starts out disjoint. But sometimes we can force them to be disjoint. Sometimes. No, if you split it up enough, you can pretty much always force them to be disjoint. So way back when in 2.2, we considered an example. There we go. And essentially the example was a certain class contains 21 students. Of these, 10 are majoring in mathematics, 13 are majoring in computer science, 5 students are not majoring in either. How many students are majoring in both mathematics and computer science? So we talked about that a while back. So we know that some students must be double majoring because essentially if we were to add the 10 people that are majoring in mathematics and the 13 people that are majoring in computer science and the 5 people who are not majoring in either of those, you get 28 people. 28 people is not 21 because we're clearly told that there's only 21 people in that class. So obviously there's some kind of overlap that's not being stated in this question. So since the set of majors, of math majors and computer science majors are not disjoint, so someone can be majoring in both, so that total number of 28 is of course going to double count some of those students. So we needed to know how many to take out. That was essentially the question we were looking at back in 2.2. But if we kind of phrase it in this idea too, let's try to find what those disjoint sets would actually be. And I'll hold on a second. No one's really scribbling, but I'll hold on a couple more seconds just in case. So if we wanted to try to think of this in terms of disjoint sets, and back in 2.2, we actually determined these numbers. So we found that the amount of students that majored in both math and computer science turned out to be 7. Now, we could work that through again, but we've technically already worked it out. So let me just say trust and believe us way back when we came to be 7. So the amount of people who studied mathematics only turned out to be 3. And then 6 people only majored in computer science. And we're told originally that only 5 people major in neither. Can I read? Apparently not. So once you kind of break it up into those different pieces, you can now think of those as 4 disjoint sets. Disjoint sets. Once you have disjoint sets, we could have added those then together to kind of triple check ourselves. Once they're disjoint, if we add them together, what is going on with my brain right now? Here we go. We get 21, which was the amount of students we were told we had. So as long as we break them into the disjoint sets, we can add them together. But when there's not disjoint pieces in there, then you got to be careful. And you can't just add them together. So in what we just talked about, we were essentially using the addition principle, but we had more than 2 sets specified in the addition principle above. So in the original addition principle that was written on the page before, it only had 2 sets in it. But here we just used it for 4. And that's because we can use it for as many sets as we want. So let's just write that down really quick. So we have a theorem that says, suppose a sub 1, a sub 2 through a sub n are pairwise disjoint finite sets. So let me finish this out really quick, and then I'll talk about that really quick in case people don't get it yet. So essentially that means that if you take any 2 sets in there and intersect them, that they'll have the empty set. As long as you're not taking the same set, so as long as I does not equal j. So if you intersect a set with itself, obviously it's not going to have the empty set because it has all the things in common with itself. But if you take any 2 sets in this list of sets, 2 different sets, and compare them, if you intersect them and you always get the empty set, then it's considered to be pairwise disjoint. Any 2 of them, intersect them, the intersection better be the empty set. And again, you can't intersect a set with itself. You can in general, just not in terms of this pairwise disjoint thing. So then essentially we can say that the cardinality of the union of all of those sets, since they're pairwise disjoint, would be essentially just the cardinality of all of them separately added together. Which is essentially just extending that addition principle that I wrote on the last slide. Because we should never take for granted things that I haven't written down yet. So technically I hadn't written it down for things that were more than 2 sets. And now we have it for more than 2 sets. So we can use it for as many sets as we need to, as long as they are all disjoint from each other. Savvy?
Okay, so what was the I equals j part?
So that essentially means that you can't, when you're considering whether they're disjoint, you're not going to intersect a set with itself. So if we're labeling all of these a sub I through a sub n, you have to take 2 sets that are different. You can't take the same set and intersect it with itself, because then the intersection wouldn't be the empty set. So that's what the I equals. Oh crap! Should be I not equal to j. Maybe. You want to make sure that you don't take the same set and intersect with it with itself. Maybe. Whoops. I was saying it right, but I wrote it down wrong. So that's the addition principle, but we'll also have, and honestly, the multiplication is going to be used more, but we also have a principle in terms of multiplication. So say we have that each box below is going to represent a letter and a number combination. So for example, the one that's marked with an X would be C3. You know, kind of some people play chess that way online or whatever. So how many possible combinations are there? Well, if you think about it, this kind of set of boxes, this is going to be 10 wide and 4 high. Now, of course, you can sit there and count all of the boxes. But what if I gave you a larger grid and you didn't want to sit there and count all the boxes till your hands fall off? Well, then you can, of course, just consider how long is it, how wide is it, and how high is it. And what do you do with those 2 numbers? You multiply them together. So we would have 10 times 4, so 40 essentially boxes, or 40 possible combinations. So again, we were kind of considering it in kind of like an area type of way instead of just counting up all the boxes. So hopefully that made sense. When we wrote down a combination, if we were to write down a combination of a letter and a number, you would write it as a coordinate pair if we were to just list out a bunch of those. So essentially you have the one set is all of the letters and the other set is the numbers that you have to choose from. And so remember, way back when we were talking about sets, we had this thing called a Cartesian product. And the elements of a Cartesian product were written as ordered pairs. So essentially, we could think of these ordered pairs as actually part of a Cartesian product between those two sets that are listed, between the set of letters and the set of numbers. So if I created a new set of the Cartesian pair between those two sets, that would essentially give me all of the choices that we were just looking at. So to write a letter number combination, you would first choose the letter and then you'd choose the number, right? Now we're going to choose these in sequence. You choose the letter and then you choose your number. So essentially we have 26 choices of, nope, that's in general. Sorry, I'm going too general here. There are 1, 2, 3, 4, 5, 6, 7, 8, 10 choices of letters and 4 choices of numbers for a total of 10 times 4 was 40 possible combinations. So essentially, what's going to happen here is we can see that essentially the cardinality of a Cartesian product, which again is exactly what this is essentially doing. It's taking a Cartesian product of a set of letters across a set of numbers, is going to be the cardinality of the first set times the cardinality of the second set. Because there are, whatever the cardinality of A is, choices for the first coordinate, and whatever the cardinality of B for the second coordinate. That's essentially the multiplication principle. You take how many choices you have for the first thing, multiply by how many things you have for the second thing, and it's going to extend to more than 2 things. So if we want to write trying to write down. So if we have A and B are finite sets, bad network quality. Come back. I know sometimes it gets weird when it does that, so I'm going to wait for that to go away. It usually goes away pretty quickly. Am I good? Nope. It still says it sucks. There, it went away. Okay. Where was I? A and B are finite sets. The number of elements, which would be ordered pairs of a Cartesian product, is going to be essentially what we literally just said. Cardinality of A times the cardinality of B. So there are going to be that many elements, and that it's essentially telling us that there's that many ways to choose the items in a sequence. So with this multiplication principle, it's usually something that you're choosing in a sequence. You're choosing one thing, and then you're choosing the next thing, and then you're choosing the next thing from that. Now, there's kind of 2 options we're going to consider. I think we only consider the one where it doesn't matter, and then in a few, I don't even know if we'll get to it today, but anyway, in a few sections from now, we'll see where we actually care about the order. But here, we kind of don't care about the order. Sure, we were listing it as a letter, comma, number. If you flip-flopped them around, it wouldn't be really the end of the world, unless someone was being really particular about it. So sometimes the order doesn't matter, and sometimes the order will, and that's going to give us completely different processes. Well, very similar, but slightly different processes. So let's say that a restaurant offers conference participants a limited 3-course menu. Each participant has a choice of soup or salad, and then they get to choose fish, chicken, or steak, and then they get to choose cake or pie. How many different combinations are there for a 3-course meal? Now, I'm going to present this in the very beginning. I'm going to draw this one time a tree, and I'm never going to draw a tree of this ever again. But so essentially, let me start the tree here, and this is going to be my root, and this is essentially no decision has been made yet. No decision. I've walked in and I've just been bombarded, and they're going to be like, soup and salad! And I'm there and I haven't decided yet. Well, I could go this way and get a soup, or I could go this way and get a salad. And then once I choose that, they make me choose again between a fish, chicken, or a steak. So once I choose soup, I could either choose, what did I just say? Fish, chicken. This is why I'm only doing this once, or steak. And I can have the, now, hold on. It's move that over a little bit. I'm going to run out of space. I essentially have the same choices for salad. I can either choose a fish, I can choose a chicken, or I can choose steak. And after I've chosen that, I still have 2 choices in each one of these for my dessert. You know, either pie or cake. Pie, cake. Pie or cake. Pie or cake. Pie or cake. And pie or cake. Okay, I'm never going to draw a decision tree ever again. But, so if you notice, we only had 3 choices here, essentially, but the tree got pretty large pretty fast, which is why I'm never going to draw one ever again in my life. But that's kind of one way you could visualize these types of things, is you have the choices, and then the choices continue to stem from your previous choices. So how many choices do we have? Well, if we count them all, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we've got 12 choices. Well, of course, we don't always want to have to just draw it out and count them up, because that's going to be really tedious really fast. But if we think about it in terms of this multiplication principle, so we have 3 choices to make. So I'm going to draw 3 blanks. Go. There we go. How many choices do we have for the first choice? Well, the first choice was soup or salad, so we only had 2 choices. How many choices did we have for the third? It was fish, chicken, or steak, so we had 3 choices for the second one. How many choices do we have for the last one? It was pie or cake, so we only had 2 choices. Multiply those all together, you get 12. So essentially, when we have these kind of sequences of choices, if you will, if we just consider the number of choices we have in each piece and multiply all of those choices together, we get the total amount of choices. Hooray! We might finish this. Questions, concerns before we do a couple examples? Okay. Well, first, let's officially write down the actual full multiplication principle and all of its generality and all that jazz. So we had more than 2 sets. Whew, and it still worked. So suppose that a sub 1 and a sub 2 through a sub n are finite sets. Then if we want the cardinality of the Cartesian product between all of those sets, you can have a Cartesian product of more than 2 things. It's just not written as a coordinate pair anymore. It's written as a coordinate list. That's not the right way to say it, but I think you know what I mean. So we take the cardinality of a sub 1, times the cardinality of a sub 2, times so on to the cardinality of a sub n. Note that in the multiplication principle, the sets do not have to be disjoint. So they can share elements all they want. We don't care. So, say I wanted to know how many different 3-letter strings can be formed from a 26-letter alphabet. How many strings of 3 letters can I form together? I don't really care about their order. I don't care about repeating things. I don't care about, having the same thing next to each other or whatever. I can have whatever strings I want. So essentially we have kind of 3 spaces to fill out for the string. Well, how many choices do we have for the first one? Well, we have 26 letters. So we have 26 choices for the first thing. How many choices do we have for the second one? Well, there's no restraints on this. I can use the same letter. So I still have 26 letters to choose from. How many choices do I have for the third one? I still don't have any restrictions, so I can choose whatever I want. So there's 26 letters. Punch that into a calculator. That is 17,576 strings of 3 letters. What if we imposed a little bit of a restriction on that? Pausing in case there's a question. So say we wanted to know instead how many different 3-letter strings can be formed from a 26-letter alphabet if no 2 adjacent letters can be the same. So you could have something like ABA, that's fine, but AAB is not fine. So you don't want 2 adjacent letters to be the same. So we still have essentially 3 blanks to fill in. How many choices do we have for the first? Well, we can choose any of the 26 letters we want. What about the next one? Well, now I can't have it be the same letter as the one before, so I only have 25 choices. Now, what about the last one? Now, it can't be the same letter in the second one, but it could be the same letter as the first one. So we're essentially we're taking away the letter from the second piece, but adding back the letter from the first option. So we're still at 25. So let me kind of put a little side note. We're adding back the first letter as an option. So in this case, there's only 16,250 choices. Savvy? That's how these go. Let's do... Well, let's take our quiz. The last thing we'll do, I'll just mention it really quick, but we'll talk about it on Tuesday, is you can also kind of mix the two. So you wanted to consider how many 3-letter strings and how many 4-letter strings. Well, you'd have to do the multiplication on each one of those two separately, and then you can add them together. What up?
I'm pretty sure I read
Oh, yeah. Didn't I do that? The homework was extended to Tuesday. So it wasn't due this past Tuesday. It was extended to next Tuesday. The one that included 3-5. That's like all of 5 questions long or something obnoxious like that. It's real short. But yeah, since you didn't know 3-5 until Tuesday, that homework had been pushed back to next Tuesday, this coming Tuesday. I'd forgotten about that. So we'll finish 4-1 on Tuesday and start 4-2. People on Blackboard, I have to push through the quiz. It's too early for it to show up on its own. So let me do that really super quick before I pass those out.